Welcome to Science with Salah Lotfy. Today, we're diving into an important research study focused on improving packaging materials using polypropylene-based biocomposites. We'll explore how hyperbranched polyamidoamine, also known as PAMAM, and gamma irradiation are used to achieve this. The research we're discussing today was conducted by a distinguished team. The lead researcher is Dr. Salah Lotfy from the Department of Polymer Chemistry at the National Center for Radiation Research and Technology, under the Egyptian Atomic Energy Authority. His colleagues include Dr. El Said Fathi and Dr. Mona El Nagar from the same department, Dr. Saber Ibrahim from the Department of Packaging Materials at the National Research Center in Egypt, and Dr. Hagar Fahmy from the Department of Advertising, Printing and Publishing at the Faculty of Applied Arts, Benha University. This research was published in the Journal of Thermoplastic Composite Materials 2024, Volume 37, Issue 1, pages 66 to 83 by Sage Publishing.
Imagine a world where packaging is not just a means to contain and protect, but also a testament to sustainability. This is the promise of biocomposites, a new class of materials poised to revolutionize the packaging industry. Derived from renewable biological sources, these materials offer a greener alternative to conventional petroleum-based plastics. They hold the key to reducing our reliance on fossil fuels and mitigating the environmental impact of packaging waste. The demand for sustainable packaging solutions is higher than ever, driven by consumer awareness and stricter regulations. With their unique blend of performance and eco-friendliness, biocomposites are uniquely positioned to meet this growing demand. Join me on this journey as we uncover the science behind these innovative materials and their transformative impact on the future of packaging. Before we can grasp the full potential of PAMAM biocomposites, we need to understand the individual components, polypropylene and polyamidoamine. Polypropylene, a thermoplastic polymer, is ubiquitous in our daily lives. It is commonly used in packaging, textiles, and even automotive parts. This versatile material is known for its low cost, high strength-to-weight ratio, and resistance to chemicals and moisture. Polyamidoamine, or PAMAM, is a type of dendrimer, a unique class of polymers with a highly branched, tree-like structure. In the context of biocomposites, PAMAM acts as a reinforcing agent, enhancing the properties of the base material, in this case, polypropylene. The secret to the remarkable performance of PAMAM biocomposites lies in the synergistic interaction between the two polymers. Polypropylene, with its long linear chains, provides the bulk properties of the material, such as flexibility and processability. PAMAM dendrimers, on the other hand, act as nano-reinforcements, enhancing the material's strength, stiffness, and barrier properties. The dendrimers, with their numerous branches and functional groups, can form strong hydrogen bonds with the PP chains. These hydrogen bonds act like tiny bridges, connecting the polymer chains and restricting their movement. This restriction in chain mobility leads to a significant improvement in the material's mechanical properties, making it stronger and more resistant to deformation. Moreover, the highly branched structure of PAMAM dendrimers creates a tortuous path for gas molecules to permeate through the material. This is particularly important in packaging applications where maintaining the freshness and quality of the packaged product is paramount. The production of PAMAM biocomposites involves a fascinating process that utilizes gamma irradiation. This technique plays a crucial role in enhancing the properties of the final material. Gamma irradiation involves exposing the PAMAM mixture to high-energy gamma rays, which are a form of electromagnetic radiation. These gamma rays interact with the polymer molecules, causing them to break apart and recombine in different ways. This process, known as cross-linking, creates new chemical bonds between the PP and PAMAM molecules. These cross-links act as additional bridges, further strengthening the interaction between the two polymers and enhancing the overall performance of the biocomposite. Gamma irradiation offers several advantages over conventional methods of cross-linking. It is a clean and efficient process that does not require the use of potentially harmful chemicals. Section 5: Mechanical Properties, the heart of packaging performance. In the realm of packaging, mechanical properties reign supreme. They dictate a material's ability to withstand the rigors of handling, transportation, and storage, ensuring the integrity and safety of the packaged product. Tensile strength, elongation at break, Young's modulus, impact strength, and tear resistance are just a few of the critical mechanical properties that determine a packaging material's performance. Among these, tensile strength stands out as a fundamental indicator of a material's ability to resist breaking under tension. Tensile strength is particularly important in packaging applications where the material is subjected to stretching or pulling forces, such as in bags, pouches, and films. A higher tensile strength translates to a more robust material, capable of enduring the stresses of packaging, handling, and transportation, without compromising the integrity of the product inside. Section 6. Tensile strength, the unsung hero of durability. Imagine a bag of coffee beans, its aroma promising a delightful caffeine boost. Now, picture that bag ripping open, spilling its precious contents and leaving you with a bitter disappointment. This unfortunate scenario highlights the importance of tensile strength in packaging. A material with high tensile strength can resist such mishaps, ensuring your coffee beans and your morning are saved from disaster. Consider the plastic films used to wrap food items, protecting them from moisture and contaminants. These films need sufficient tensile strength to withstand the tension applied during the wrapping process and maintain their integrity throughout the product's shelf life. Similarly, the plastic bags used to carry groceries rely on their tensile strength to bear the weight of the contents without tearing. The incorporation of PAMAM dendrimers into polypropylene significantly enhances its tensile strength. Section 7. Beyond the basics, other mechanical properties. While tensile strength takes center stage, it's not the only mechanical property that matters in packaging. Elongation at break, for instance, measures how much a material can stretch before it breaks. This property is crucial for packaging that needs to accommodate variations in shape or volume, such as flexible pouches for liquids or shrink films for securing products. Then there's Young's modulus, a measure of a material's stiffness or resistance to deformation under stress. Impact strength, as the name suggests, reflects a material's ability to withstand sudden impacts or shocks. And finally, tear resistance measures a material's ability to resist tearing or propagation of a tear once it's initiated. In this section we explore real-world applications and see where biocomposites truly shine. The enhanced mechanical properties of PAMAM biocomposites, particularly their impressive tensile strength, open up a world of possibilities in the packaging industry. These materials are poised to revolutionize the way we package and protect a wide range of products, from food and beverages to pharmaceuticals and electronics. Imagine a future where your favorite snacks come in bio-based, compostable pouches that are just as durable and convenient as conventional plastic packaging. These pouches, made from PAMAM biocomposites, would not only protect the contents but also decompose naturally after use, reducing the burden on landfills and contributing to a more sustainable future. The enhanced barrier properties of these biocomposites make them ideal for packaging sensitive products that require protection from moisture, oxygen, and light. Furthermore, the lightweight nature of these biocomposites can lead to significant reductions in transportation costs and fuel consumption. In Section 9, we delve into a sustainable future by examining the environmental impact. The environmental impact of packaging waste has become a pressing global concern. Traditional petroleum-based plastics, while durable and versatile, pose a significant threat to our planet. They take hundreds of years to decompose, polluting our landfills, oceans, and ecosystems. Biocomposites, with their origins in renewable biological sources, offer a beacon of hope in this regard. PAMAM biocomposites, in particular, can be engineered for biodegradability, meaning they can break down naturally over time, leaving behind minimal environmental impact. This shift towards sustainable materials aligns with the growing global movement towards a circular economy, where resources are used and reused in a closed loop, minimizing waste and environmental impact. Section 10 focuses on challenges and opportunities as we look down the road ahead. While the future of biocomposites in packaging appears bright, some challenges remain. Scaling up production to meet the demands of the global packaging industry while maintaining cost-effectiveness is a key hurdle. Research and development efforts are crucial to optimize production processes and make these materials more accessible to a wider range of industries. Another challenge lies in ensuring the compatibility of biocomposites with existing recycling streams. Designing these materials with end-of-life management in mind is crucial to realizing the full potential of a circular economy. Despite these challenges, the opportunities presented by biocomposites in packaging are vast. In our final section, we conclude by embracing the future of packaging. Biocomposites, particularly those based on polypropylene and PAMAM dendrimers, represent a paradigm shift in the packaging industry. They offer a unique blend of sustainability, performance, and versatility, addressing the growing demand for packaging solutions that are both functional and environmentally responsible. As we navigate the challenges of a rapidly changing world, embracing sustainable materials and practices is no longer an option but a necessity. By embracing innovation, supporting sustainable practices, and making conscious choices, we can pave the way for a future where packaging is no longer a threat to our environment but a testament to our commitment to a healthier planet.
Packaging plays a crucial role in our everyday lives. It protects our food, transports our goods, and even influences our purchasing decisions. But traditional packaging materials, often derived from fossil fuels, come with a significant environmental cost. Scientists and engineers are constantly striving to develop packaging materials that are not only eco-friendly but also possess superior mechanical properties. Polypropylene, a versatile plastic, has emerged as a frontrunner in this quest. It's lightweight, durable, and easily recyclable. Researchers have been exploring ways to enhance the mechanical strength and thermal stability of polypropylene, making it even more suitable for demanding packaging applications. Imagine a world where your cereal box is not only protecting your breakfast, but also contributing to a healthier planet. This vision drives the relentless pursuit of innovative packaging solutions, and polypropylene bio-composites stand as a testament to this ongoing revolution in material science. The creation of polypropylene biocomposites involves a fascinating blend of natural and synthetic materials. Researchers begin by carefully selecting natural fibers, often derived from plant sources known for their strength and resilience. These fibers are then combined with polypropylene, the workhorse polymer of the packaging industry, to form a composite material that boasts enhanced properties. However, simply mixing these components isn't enough to unlock their full potential. This is where hyperbranched polyamidoamine, or HBPAA, comes into play. HBPAA acts as a compatibilizer, a molecular bridge between the natural fibers and polypropylene. It improves their interaction, ensuring that the fibers are evenly distributed throughout the material and effectively transfer their strength to the polymer matrix. To further enhance the properties of these biocomposites, researchers employ a technique called gamma irradiation. This controlled exposure to gamma rays initiates a process called cross-linking, where the polymer chains within the polypropylene become interconnected. The incorporation of natural fibers and the application of gamma irradiation yield remarkable improvements in the mechanical properties of polypropylene biocomposites. Tests have shown that these materials exhibit significantly higher tensile strength, meaning they can withstand greater pulling forces before breaking. This enhanced strength translates into more durable packaging that can protect its contents more effectively. Moreover, the biocomposites demonstrate increased flexural strength, indicating their ability to resist bending and breaking under pressure. This property is particularly important for packaging applications where the material needs to maintain its shape and integrity even when subjected to external forces. In addition to mechanical strength, the thermal stability of these materials also sees a significant boost. This means they can withstand higher temperatures without deforming or degrading. The enhanced thermal stability ensures that the packaging remains intact and protects the food even when exposed to heat during transportation or storage. The combination of improved mechanical strength and thermal stability makes polypropylene biocomposites ideal for a wide range of packaging applications. The application of polypropylene biocomposites in food packaging is particularly promising. These materials offer a unique combination of sustainability and performance that aligns perfectly with the demands of the food industry. They provide a robust barrier against moisture, oxygen, and other external factors that can compromise the freshness and safety of food products. Imagine a takeaway container for your favorite hot meal that not only keeps your food warm and fresh, but is also biodegradable, breaking down naturally after use. This is the kind of sustainable solution that polypropylene biocomposites offer. They have the potential to revolutionize the way we package and consume food, reducing our environmental impact without compromising on convenience or quality. Furthermore, the use of natural fibers in these biocomposites adds another layer of sustainability. Unlike traditional plastics derived from fossil fuels, these materials utilize renewable resources, reducing our dependence on finite resources and contributing to a circular economy. The research and development of polypropylene biocomposites represent a paradigm shift in the packaging industry. This innovation is driven not only by the need for more sustainable alternatives, but also by the pursuit of materials with enhanced performance characteristics. The success of this endeavor signifies a broader trend in materials science, one that emphasizes both environmental responsibility and technological advancement. The adoption of polypropylene biocomposites in packaging has the potential to transform the entire supply chain. From the sourcing of raw materials to the manufacturing processes and ultimately the disposal and recycling of packaging waste, every stage stands to benefit from the sustainable nature of these materials. Imagine a future where packaging, instead of ending up in landfills, becomes a valuable resource that can be returned to the ecosystem safely. This vision of a circular economy where materials are reused and recycled is a key driver behind the development of sustainable packaging solutions like polypropylene biocomposites. The revolution in packaging has begun, and it's powered by the remarkable potential of materials science.
Polypropylene, or PP, is a versatile polymer widely used in various industries, from packaging to textiles. However, its applications are sometimes limited by its inherent properties, such as moderate mechanical strength and susceptibility to degradation. One such approach involves combining PP with polyamidoamine, or PAMAM, dendrimers, and treating the composite with gamma irradiation. This method has shown significant promise in enhancing the mechanical, thermal, and barrier properties of PP, broadening its potential applications. Today, we delve into the fascinating world of PP-PAMAM composites, specifically focusing on the impact of PAMAM additives and gamma irradiation. Join us as we unravel the intricacies of this revolutionary material and its potential to shape the future of various industries. The incorporation of PAMAM dendrimers into the PP matrix introduces a fascinating interplay of molecular interactions. These dendrimers, with their unique branch structure and numerous functional groups, act as reinforcing agents within the polymer matrix. They interact with the PP chains, forming strong hydrogen bonds and enhancing the overall cohesiveness of the material. Gamma irradiation further amplifies these enhancements by inducing cross-linking within the PP-PAMAM composite. This process creates covalent bonds between the polymer chains, effectively forming a more interconnected and robust network. The cross-linking process is akin to building bridges between individual polymer strands, making it more difficult for them to slide past each other under stress. This increased resistance to molecular movement translates to improved mechanical properties and enhanced resistance to degradation. The combined effect of PAMAM additives and gamma irradiation is not merely additive but synergistic. The dendrimers act as nucleation sites for cross-linking, promoting a more uniform and effective cross-linking process throughout the material. This synergistic effect leads to a significant improvement in the material's properties, exceeding what would be achieved by either modification alone. The ability to fine-tune the material's properties by adjusting the concentration of PAMAM dendrimers and the dosage of gamma irradiation offers a high degree of control over the final product. For instance, a higher concentration of PAMAM dendrimers and a higher irradiation dose might be desired for applications demanding exceptional strength and durability. Stress strain curves provide a visual representation of a material's mechanical behavior under tensile stress. Analyzing these curves offers valuable insights into the material's strength, stiffness, and ductility. When comparing the stress strain curves of unirradiated and irradiated PP-PAMAM composites, distinct differences emerge, highlighting the profound impact of irradiation on the material's mechanical properties. unirradiated PP-PAMAM composites typically exhibit a typical stress-strain curve for a semi-crystalline polymer. The curve shows an initial linear elastic region, where the material deforms elastically and returns to its original shape upon removal of stress. As the stress increases, the material enters the plastic deformation region, where it undergoes permanent deformation. Finally, the curve reaches the ultimate tensile strength, representing the maximum stress the material can withstand before failure. In contrast, irradiated PP-PAMAM composites demonstrate a marked improvement in mechanical properties, evident in their stress-strain curves. The irradiated samples exhibit a higher yield strength, indicating greater resistance to deformation under stress. This enhanced yield strength is attributed to the cross-linking induced by gamma irradiation, which restricts the movement of polymer chains and enhances the material's ability to withstand applied forces. The combination of higher yield strength and tensile strength in irradiated PP-PAMAM composites underscores their potential for applications demanding robust mechanical performance. The mechanical properties of PP-PAMAM composites are significantly enhanced by the synergistic effects of PAMAM dendrimers and gamma irradiation. Tensile strength, a measure of a material's resistance to breaking under tension, sees a substantial increase in irradiated composites. This improvement is attributed to the cross-linking of polymer chains, creating a more tightly bound and robust network structure. The cross-links act as anchors, preventing the chains from easily sliding past each other and increasing the material's ability to withstand tensile stress. Elastic modulus, a measure of a material's stiffness or resistance to deformation under stress, also experiences a noticeable improvement in irradiated PP-PAMAM composites. The increased stiffness is a direct result of the restricted chain mobility caused by cross-linking. The interconnected network structure limits the chain's ability to stretch or deform under stress, leading to a higher elastic modulus. This enhanced stiffness translates to a material that can maintain its shape and structural integrity even under significant loads. Elongation at break, a measure of a material's ductility or ability to stretch before breaking, is another crucial mechanical property that is influenced by irradiation. Interestingly, irradiated PPAMAM composites may exhibit a slight decrease in elongation at break compared to their unirradiated counterparts. The overall improvement in mechanical properties observed in irradiated PP-PAMAM composites makes them highly attractive for various applications. Morphological studies using scanning electron microscopy, or SEM, provide valuable insights into the microstructure of PP-PAMAM composites and reveal the impact of additives and irradiation. SEM images of unirradiated PP typically show a relatively smooth surface with distinct spherulites, which are characteristic crystalline regions within the polymer matrix. The addition of PAMAM dendrimers introduces subtle changes in the morphology, often appearing as small, dispersed particles within the PP matrix. Upon gamma irradiation, significant changes in the morphology become evident. The SEM images of irradiated PP-PAMAM composites often reveal a more compact and interconnected structure. The spherulites may appear smaller and less defined, indicating a higher degree of cross-linking and a reduction in the overall crystallinity of the material. This change in morphology is consistent with the observed enhancement in mechanical properties, as a more interconnected structure leads to greater strength and stiffness. Hardness tests, such as the Shore hardness test, provide a measure of a material's resistance to indentation. Irradiated PP-PAMAM composites generally exhibit higher hardness values compared to their unirradiated counterparts. This increase in hardness is attributed to the cross-linking process, which creates a more rigid and interconnected network structure, making it more difficult for the indenter to penetrate the material's surface. The enhanced surface hardness resulting from irradiation is beneficial in applications where resistance to scratching, abrasion, or wear is essential. Safety is paramount, especially when dealing with materials intended for food packaging or other sensitive applications. Chemical migration, the transfer of substances from packaging materials into food, is a critical concern. To ensure consumer safety, rigorous testing and adherence to regulatory standards are essential. PP-PAMAM composites, particularly those intended for food contact, undergo stringent evaluation to assess potential chemical migration and ensure compliance with safety regulations. One of the key aspects of safety testing involves evaluating the potential for chemical migration from the packaging material into food simulants. These simulants mimic the properties of different types of food, such as fatty, acidic, or aqueous foods. The amount of any substance that migrates from the packaging into the simulant is carefully measured and compared to established migration limits. These limits are set by regulatory bodies to ensure that the amount of any substance migrating from the packaging is below levels that could pose a health risk. Gamma irradiation, while beneficial for enhancing material properties, can raise concerns regarding the potential formation of harmful byproducts. However, studies have shown that gamma irradiation, when applied within specific dose ranges, does not lead to the formation of harmful substances in PP-PAMAM composites. The irradiation process is carefully controlled to ensure that the material remains safe for its intended use, particularly in food packaging. Regulatory compliance is another crucial aspect of ensuring the safety of PP-PAMAM composites. These materials must meet the stringent requirements set forth by regulatory agencies worldwide, such as the European Food Safety Authority and the U.S. Food and Drug Administration. The remarkable properties of PP-PAMAM composites, enhanced by the synergy of PAMAM dendrimers and gamma irradiation, open up a world of possibilities across various industries. Their improved mechanical strength, thermal stability, and barrier properties make them ideal candidates for a wide range of applications, revolutionizing sectors such as food packaging, automotive manufacturing, and biomedical engineering. In the realm of food packaging, PP-PAMAM composites offer a promising alternative to conventional materials. Their enhanced barrier properties help extend the shelf life of food products by preventing the ingress of moisture, oxygen, and other gases that can lead to spoilage. The improved mechanical strength ensures the packaging's durability, protecting the contents during transportation and handling. Furthermore, the safety of these composites for food contact, validated through rigorous testing and regulatory compliance, makes them a reliable choice for preserving food quality and safety. Beyond food packaging, PP-PAMAM composites find utility in the automotive industry, where lightweight and high-performance materials are highly sought after. Their enhanced mechanical properties, coupled with their lightweight nature, make them suitable for manufacturing various automotive components, such as interior trims, dashboards, and door panels. The use of these composites can contribute to reducing vehicle weight, leading to improved fuel efficiency and reduced emissions. The biomedical field also benefits from the unique properties of PP-PAMAM composites. The journey of PP-PAMAM composites is far from over. As research and development efforts continue, new frontiers emerge, promising further advancements in material science and unlocking even greater potential for these versatile materials. One exciting avenue of exploration lies in tailoring the properties of PP-PAMAM composites by functionalizing the PAMAM dendrimers with specific molecules or nanoparticles. This functionalization can impart desired properties, such as antimicrobial activity, flame retardancy, or enhanced barrier properties, expanding the application possibilities even further. Another promising research direction involves exploring the use of alternative irradiation sources, such as electron beam irradiation or ultraviolet (UV) irradiation. These alternative methods offer potential advantages in terms of energy efficiency, processing time, and environmental impact. Investigating the effects of these alternative irradiation sources on the properties of PP-PAMAM composites could lead to the development of more sustainable and efficient processing techniques. Furthermore, incorporating computational modeling and simulation techniques into the design and development process holds immense potential. By simulating the behavior of PP-PAMAM composites at the molecular level, researchers can gain a deeper understanding of the structure-property relationships and optimize the material's properties for specific applications. The future of PP-PAMAM composites is bright, driven by ongoing research, technological advancements, and a growing demand for high-performance materials.